All right, so let's talk about tension. What is tension? Tension is an intermolecular force that exists inside of ropes and strings and other kind of materials that you can pull on, but that also are flexible. So here's the idea. The purpose of tension is to maintain the integrity of the string or the rope. No stretchy, no breaky, okay? Same length, and it's not gonna break. So that's the idea. Now, I can't push you with a string, all right? If I've got a string, I try to push on it, well, it's just gonna go limp. I can only pull with a string. So that means that whenever you see a string or rope tied to something, it's always pulling. It cannot push. And that seems like a really, really, really simple idea, but you wouldn't believe the number of mistakes that I've seen where people aren't thinking about it that way and they get this other kind of idea that goes into their minds and then everything's just wrong. All right, so let's see how this works. So first off, I want to imagine that I've got a rock that I'm swinging in a circle, a vertical circle like this, all right? And I want to determine what is the tension in this rope when the rock's at the bottom and when the rock's at the top of the circle. All right, so let's do the bottom first. Well, of course, we're going to start with a free body diagram. I mean, geez, what are we, idiots? So we'll start with the free body diagram and we'll say, all right, what about the acceleration? What acceleration does this rock experience at the bottom? Well, it's got to have an acceleration towards the center of the circle that's v squared over r. And that's because it's moving in a circle. What do you want? So we've got an acceleration that's going up in this case, and it's v squared over r. All right? So that means that the tension minus mg must be ma, m v squared over r. So that gives us a tension of the weight plus mv squared over r. So at the bottom of the circle, the tension is actually larger than the weight. All right. What happens at the top? All right. Now this is where people get all messed up. All right. At the top, where's the string? Well, it's like that. So what direction is the tension force in? Strings can only pull. It's pulling down. It can't do anything else. That string can't push it up. All right? The string would just go limp before it did that. So at the top, we have a tension force acting down. And what about the weight? Does the weight act up now? No. The weight always acts down towards the center of the earth. So this is a kind of strange looking free body diagram. Everybody's pulling down. Well, the acceleration's down too. V squared over r, just like it was before, except in this case it's down because it's got to be directed towards the center of the circle. All right, so what do we got? Well, we've got tension plus mg has to equal ma. So that means that the tension is equal to mv squared over r minus mg. All right, now this is an issue. This minus sign means that it could be the case that this tension was negative. But what would that mean? Well, that would mean I'm trying to push with a string. You're not allowed to push with a string. You can only pull with a string. So that means that this tension got to be positive. So that means that the speed has to be bigger than the square root of r times g. This is the minimum speed at which you can get the rock to go in this circle. If you try to go slower than that, it'll get up to a certain point, and then the string will just go, just fall, all right? And then it won't make it to the top because there's not enough speed to do it. All right, so that's the idea. Let's look at another problem involving a string. So here I've got a mass m and a mass 1/2 m. Mass m is sitting on a frictionless countertop, and mass 1/2 m is pulling down like this. And the two masses are connected by a string which runs over a pulley. All right, now what's the purpose of a pulley? An ideal pulley does nothing more than change the direction of the tension. That's the only purpose. So here, the tension's pulling that way because the string's there and you got to pull, right? Here, which direction is the tension in? All right, this is another place that I've seen a lot of mistakes. People look at this string and they're like, well, geez, the tension's going in that direction, so the tension must always go in that direction. It must be pushing down. But no, you're not allowed to push with a string. You can only pull. So the tension must be pulling up on this guy. Opposite directions, but you can't argue with a string can't push. Can only pull. All right, so let's draw some free body diagrams. Try to determine the acceleration of this system. All right, well, we've got two objects here. We've got mass m and mass a half m. All right, so let's look at mass m. Well, what are the forces acting on it? Well, geez, it's got a weight, like everybody does. It's also on the table. Now, the table doesn't want it to fall through it, so the table is going to put a normal force on it to push it up. Remember that the purpose of a normal force is to maintain the integrity of a solid object. So you're pushing on it and it fights back. All right, so we'll have a normal force here, which is however big it needs to be to ensure that there's no acceleration into the table. And then we've got the force acting this way, tension, T. All right, so we've got this tension that's inside of this string. So how is this tension T associated with the tension that's acting on a half m? Well, let's see. All right, on a half m, we've certainly got our weight, 1/2 mg. And then what about the tension force? Well, that's going to certainly be acting up. And what's the relationship between this tension and this tension? Well, they're obviously in different directions, but they're associated with the same string. Now, the way that ideal strings go is that the tension throughout them has to be the same. Now, this isn't actually true in real strings because the tension will be a little bit higher at the bottom here. I'm sorry, at the top here, because that tension has to support the weight of the string. But you know what? Strings don't weigh very much. Let's just ignore that. And so what we'll do is we'll say that this is the same magnitude force, T, as this one. All right, what about the accelerations? Well, what do we expect? I mean, we expect this mass to go to the right, this mass to go down. So we'll have acceleration here, and we'll have acceleration here. Okay, now, what's the relationship between those two accelerations? Well, the string isn't allowed to change its length. The string is what we call inextensible. All right, so it can't change its length. So that means that if these guys are accelerating, they got to accelerate at the same rate. So these accelerations have to have the same magnitude. All right, so let's see what's going on. All right, Newton's second law, these two forces cancel. So I might as well not even have written them down. I wanted to be correct, so I wrote them. But a normal force is just going to cancel the weight because there can't be any acceleration vertically. All right, what about horizontally? Well, we'll have T equal ma. All right, that's easy enough. And then here we'll have 1/2 mg minus T equals 1/2 m times a. All right, these two equations are very, very, very easy to solve. I'm going to show you a nice technique. All we're going to do is we're going to take these two equations and we're going to add them together. And we can, of course, do that. I mean, if this one's true and that one's true, then the sum of them is going to be true too. But look what's beautiful about this. The tension is going to cancel. So that means that we'll have 1/2 mg equals, and let's add these two together. Well, this is going to give a half plus 1. Well, that's 3/2 ma. And look how beautiful that is. M cancels. The 2 cancels. A is 1/3 of the acceleration due to gravity. So this system is going to accelerate at 1/3 of the acceleration due to gravity. Now, if we wanted to, we could determine the tension just by saying, well, geez, the tension is m times 1/3 the acceleration due to gravity. So the tension is going to be 1/3 mg, 1/3 of the weight of that mass. All right, let's do one more situation. And this is a standard situation with pulleys. We got a pulley system here. We've got 2 pulleys. We've attached this one to the ceiling. And then we are winding a string around. We attached it to the bottom of that pulley, and we ran it around that pulley. Then we attached this pulley to a mass. All right. We want to know what force do I have to pull with in order to support this mass. All right, so let's go ahead and determine first off what's going to be the tension in this string. Now remember, this string is all one string. That means its tension has to be the same throughout. Well, I'm pulling with F here, so that means the tension in this string has to be F all the way through. All right, now let's draw a free body diagram of this pulley. All right. Well, what force is pulling down on that pulley? Well, it looks to me tension 2 is. All right. Now, tension 2, of course, just equals mg because that's got to support the weight of that guy. So this is just mg. All right. Here's the tricky part. What force is acting up on this pulley? Well, the string is here, and strings can only pull. So it must be pulling up. But the string's also here. Now, this is the weird part that throws people off. And they're thinking, well, the string can't pull twice. Yes, it can. The string can pull twice, and it will. It's attached here, and it's attached here. So it's pulling up both sides. So that means I've got F and F again. All right? So that means that 2 times F in equilibrium has to equal mg. So that means the force that I need to supply is only a half of the weight of the thing that I'm trying to support. So essentially, by using this pulley system, I have doubled my force, right? So I'm supporting something that's twice as heavy as the force that I need to apply to support it. All right, that's the idea of a pulley system. In general, you'll multiply your force by the number of pulleys. Here we've got 2 pulleys, so we multiply it by 2. If we had 50 pulleys, we would multiply it by 50. All right, one other real quick thing. Let's determine what this tension is right here. All right, so that tension, we're going to draw a free body diagram of this up top pulley. So pulling up, tension 1. What's pulling down? All right, again, whenever you see a string, it is pulling. All right, it's pulling. So I see a string. I see one there, and there's 3 tensions pulling down on this guy. So this will be 1, 2, and 3. F, F, and F. So that means tension 1 has to be 3F, which is 3 halves of mg. And that's essentially how every single pulley problem goes. They're all really, really, really easy once you recognize that strings can only pull. And that's tension.